Hi, my name is Elizabeth, and this is my presentation on cyber warfare, steganography versus steganalysis. So the idea behind steganography is not new. Hiding data by embedding it in different forms has been going on for centuries. For example, in ancient Greece, they tattooed the shaved heads of messengers with messages, and in both world wars, they used invisible ink to send messages. As we can see, both of these methods intended to secretly communicate messages by concealing the existence of the message itself. Can you think of any other examples of secret communication like this throughout history? Then, the rise of the internet in the 1990s led to an interest in using modern technology to hide data. This came in the form of using digital media like images as a disguise, hiding data using computers and signal processing techniques, and then distributing all that stego content throughout the internet. Steganography rose in popularity for secret communication using data embedding. However, this did lead to concerns about potential misuse of steganography with malicious intentions and how that could threaten the field of information security. This concern then led to the rise of Steganalysis, which is the detection of embedded information as a field whose goal it was to defeat steganographic techniques. However, trying to detect hidden data concealed in millions of different media items spread all throughout the internet is an extremely difficult task. This began the battle between steganography and steganalysis that we will cover in this presentation. One thing I would like to note is that this paper was published in 2004, and thus there have likely been many developments to both steganography and steganalysis in the last 20 years that may render some of this paper outdated. However, this paper provides a solid overview of the basics behind both of these fields that still make it a very interesting read. In this presentation, we will cover steganography and steganalysis. The core message that this paper communicates is as thus. For every method being developed to hide information in multimedia data, an equal number of methods are being developed to detect and reveal its secrets. This statement highlights the ongoing battle between the fields of steganography and steganalysis. As one field advances, so does the other. However, in order to understand the cyber war going on between these two fields, we must first understand what steganography and steganalysis are. So we will start with steganography. The idea behind steganography is hiding data in plain sight. It can come in the form of stego images, like the one shown here, where a cover image is used as a disguise for the embedded data to conceal the fact that there's any hidden data in the first place. Modern-day steganography consists of using digital media content, also known as cover media, and signal processing techniques to disguise embedded data, and then distributing that stego media throughout the web. The most popular cover media for steganography are images in bitmap form, or BMP, compressed format, JPEG, or GIF format, which are used for palette images. Then, in order to insert secret messages into these cover media, we can use different insertion methods such as substitution, adjustment, and addition. For example, one adjustment method is quantization index modulation, or QIM, which uses different quantizers to carry different bits of secret data. So who here has heard of watermarking? Many of us have probably encountered watermarking when looking for images online and finding a great one, but then there's an annoying mark in the form of a symbol or a text across it that obscures the image, as we can see here. This is actually a form of embedded data. So one way to gain a deeper understanding of steganography is to compare it to a form of embedded data that is more commonly seen, such as watermarking. So first, in steganography, the embedded data is the message that needs to be communicated, while the object or cover media serves as a disguise for that data. However, in watermarking, the embedded data gives the copyright protection to the object, while the actual intended communication is the object itself. Then in steganography, in order to be successful, the existence of the embedded data should not be known. Undetectability is the main concern. Then in watermarking, the watermark is usually public knowledge and openly declared in its existence. Then finally, for steganography, once the presence of hidden data is revealed, the goal of steganography is useless, even if the message itself is still encrypted using cryptographic techniques. For steganography, the main goal is to avoid detection in the first place. So robustness against attacks isn't a huge concern for steganography. Then for watermarking, if the watermark, which is the embedded data, is removed, then the host is useless. Thus, watermarks must be robust against attacks. So here I grabbed a table from the paper that compares watermarking and steganography in many aspects. They also add a measurement for the importance of certain criteria to the two fields using the number of plus signs. So I wanted to point out a few interesting observations from this table. As we can see, for steganography, the most important points are its perceptual and statistical invisibility, while for watermarking, the most important aspect is its robustness against hostile removal, destruction, or counterfeiting. This holds against our understanding of steganography and watermarking from the previous slide. Then we can see that watermarking also holds perceptual invisibility in a high regard, but not statistical invisibility. And this makes sense, as perhaps watermarks don't always need to be visible to the naked eye, but also don't need to go undetected in statistical analysis, since its presence does not have to be a secret. Then, steganography does not hold any regard for robustness against removal, destruction, or counterfeiting, but does give some thought to resistance against normal signal processing. And this holds, as we know, steganography's main goal is to avoid detection and not to avoid attack. So it doesn't need to be robust, but signal processing would involve trying to detect hidden data, so it should give some thought to that. Then, both steganography and public watermarking both consider extractability and detectability without cover object to be important, which also makes sense, as one should be able to extract the embedded data to confirm copyright or to read the hidden message. Overall, both fields have many similarities and differences in how they treat their embedded data. So I also wanted to compare steganography and cryptography. So cryptography does not conceal the communication itself, but scrambles the data to prevent unauthorized entities from understanding its content. Steganography, as we know by now, involves a secret communication by disguising the existence of hidden data in digital media. So those who participate in secret communication can and should always apply cryptographic algorithms to the data to conceal its meaning before using steganography to embed it in order to achieve that extra layer of security. Thus, if steganography fails and the existence of hidden data is revealed, the contents of the message itself still remains secure. Now I want to get into the actual implementation of steganography. And there are many methods that we can use, such as LSB modification, masking approaches, transform domain techniques, image compression algorithms, and spread spectrum techniques. And while these are not the only methods out there, they are the ones that we will cover in this presentation. So here we're going to cover how to embed data into an image by modifying the least significant bit of the pixel values in the space domain of an image. So on the left, we have the bit planes of the grayscale image, with the most significant bit plane on the top and the least significant bit plane on the bottom. And then on those, the dark gray boxes represent the binary value 0, and the lighter yellow boxes represent the binary value 1. On the right, at the top image, we see the LSB plane of the cover image we are using, so that has none of the embedded data in it. And then the middle image on the right is the embedded data that we want to communicate. So we will replace the LSB plane of the cover image with the embedded data, and thus the embedded data becomes the LSB plane of the resulting stego image, which is the cover image with the steganographic data embedded in it. For this method, on average, 50% of the least significant bits, or LSBs, are flipped when this occurs. So as we can see in the bottom image to the right, the blue dots represent all the bit values that were flipped as a result of the replacement between the original LSB plane of the cover image and the embedded data. And then the result of this is a Stego image that is visually identical to the cover image. This method, LSB embedding, is vulnerable to image processing, however, which is something to consider. So as shown here, this Stego image is the result of LSB embedding. Can anyone see the data hidden in this image? And that answer is no. The Stego image is visually identical to the cover image, and thus we have successfully hidden the existence of the secret communication and performed steganography. While we won't go as into depth with these other steganographic techniques as we did with LSB embedding, I wanted to briefly mention how each one works. So first, masking approaches. With this, pixel values in masked areas are raised or lowered by some percentage, and if that percentage is sufficiently small, it can render the change invisible. And then next, transform domain techniques. This involves data embedding in the transform domain of an image. The techniques involved with this are discrete cosine transformation, or DCT, discrete wavelet transformation, or DWT, and discrete Fourier transformation, or DFT. Overall, with this method, because the data is embedded in the transform domain, there is better resistance against signal processing since the data is in a more robust area and is spread across the entire image. With compression algorithms, the goal is to integrate data embedding with image compression algorithms like JPEG. These techniques are enticing because JPEG images are very common on the internet. And then finally, spread spectrum techniques. With this technique, the secret data is spread throughout the cover image based on spread spectrum techniques. And white noise storm is a popular tool for this technique. So this paper also provides some really cool steganographic tools that you can use to perform steganography. And I captured that table from the paper itself on the right there. However, some of these links in this table are outdated and do not work. Therefore, I wanted to provide a list of the working links and some updates to the table on the left here. So the links for MP3 Stego and Steganos do work, and so does the outguess link. However, the old link for outguess will redirect you to the new one that I provided here. Also, the steganography tool table works as well, which is that link you can find at the bottom of that blue table here. However, their website does say that they are migrating to an updated steganography software list at the link that I provided at the bottom of the list on the left. Overall, there are 3 requirements that must be satisfied for any steganographic system: security of the hidden data, size of the payload, and robustness against attack. So first, security of the hidden data. The hidden contents must be invisible to both the naked eye and statistical detection. A system is considered secure if it is impossible for an attacker to detect the presence of hidden content by any means. And then the size of the payload. So hiding data requires sufficient data embedding capacity, which is usually contradictory to security, and thus there must be a trade-off between the two. And then finally, robustness. So robustness against attack is not a top priority for steganography, as avoiding detection at all is the main priority. However, being able to withstand attacks like JPEG coding is a very desirable feature to have. So next we will finally introduce Steganalysis. So Steganalysis refers to the detection of the presence of hidden data in a given image. And Steganalysis has 2 main techniques: visual analysis and statistical analysis. Visual analysis attempts to reveal the presence of hidden data through inspection with the naked eye or with computer assistance. A computer can help decompose an image into bit planes, and then any unusual appearance in the LSB plane would indicate the existence of secret data. Statistical analysis is more powerful since it can detect steganographic embedding by revealing tiny alterations in the image's statistical behavior. This table highlights some of the specific Steganalysis methods and specific steganographic techniques that they target. For example, we can see that RS Steganalysis at the top there targets LSB modification, which is the steganographic technique that we covered earlier. Then we can also see that palette checking directly combats steganography in palette images, which are usually in that GIF format, which detects anomalies in palettes due to color singularities caused by embedded data. And then we can also check for JPEG compatibility with Stego images that use JPEGs as cover images. And this is because JPEG images have a known and specific structure, and when data is embedded, it changes the JPEG signature slightly, thus making the Stego image vulnerable to detection. And then histogram analysis targets QIM embedding, which we will show an example of later. Overall, there are many ways of embedding data, and each method alters the image in different ways, producing a variety of results. This then causes more universal methods of Steganalysis, like the one at the bottom of the table, universal blind detection, that tries to target various steganographic techniques to be less effective than Steganalytic methods aimed at specific types of embedding. Here, we will observe the LSB planes of the cover image, the Stego image, and a sequentially embedded Stego image, and observe the differences and see how a visual analyst might be able to detect hidden data. So we will start on the left with image A, which is a Stego image that we saw earlier, which was the result of LSB embedding and is visually the same as the cover image used, which were two palm trees, as we can see here. And then as we go right, image B shows the LSB plane of the original cover image, and we can observe a few features that align to areas with smooth and saturated colors. And keep in mind that image B does not have any embedded data. Then in image C, we can see the LSB plane of the Stego image, which does contain embedded data that has been scrambled and spread over the bit plane to obscure the original features. While this Stego image's LSB plane is visually extremely similar to the LSB plane of the cover image, we can see some clear differences. Can you point them out? Those observations illustrate how one might analyze the LSB plane to detect hidden data. And then, as we move on to image D on the right, we can see what might happen if the data was embedded sequentially, which would result in the message data taking up only the red and a portion of the green planes, with the rest of the LSB plane padded with zeros. This emphasizes the importance of scrambling and spreading the embedded data over the LSB plane in order to be successful in your steganographic attempts, as image D is extremely different from the original LSB plane and obviously has embedded data. Overall, more sophisticated embedding schemes that select busier areas and pad with random sequences that have the same statistical property as the cover image would make visual analysis of the LSB plane much more difficult than what we see here. And then here, in this slide, we have an example of statistical analysis with this histogram analysis for a steganographic technique called QIM, or quantization index modulation. The QIM technique uses a number of quantizers to embed data into the cover image, so the sample values or certain coefficients show signs of discreteness. Now, we don't have to fully understand how QIM works to understand that the detection of this form of embedding originates from the distinct footprint it leaves behind, which is the discreteness of the coefficients. And then a histogram analysis can be used to reveal such a signature. The left histogram represents the distribution of a particular group of coefficients taken from the cover image, and then the right histogram represents the distribution of a particular group of coefficients from a stego image. And the discreteness of the histogram on the right is a clear sign of QIM embedding. And thus, we have used statistical analysis to detect hidden information from QIM embedding. While we have focused on steganography as a field applicable to anti-terrorist and intelligence operations and how that may impact the information security field, steganography also has many other more peaceful applications. We can use steganography for many civilian applications, such as in-band captioning and integrating media for storage, management, and transmission purposes. We can also embed function executables, do error correction, and implement version upgrading. Overall, steganography has a wide range of applications that can apply to everyday life. Overall, Steganalysis must keep evolving in order to break steganographic techniques. However, steganography will also continue to evolve. This battle between sending hidden messages and detecting hidden messages has a significant impact on the field of information security. For example, countermeasures against Steganalysis are emerging in the form of tools that can withstand visual and statistical attacks. Thus, we must remain vigilant, as what is secure today may be broken tomorrow, and tools that can detect hidden content today could be useless tomorrow. And this connects us back to that core message: for every method and tool being developed to hide information in multimedia data, an equal number of methods and tools are being developed to detect and reveal its secrets. In the last 20 years since this paper was written, many developments to the field of information hiding with steganography and information detection with Steganalysis have probably been made, and I'm positive this will continue into the future. So thank you for listening to my presentation, and I hope it was informative. If you're interested in reading the paper associated with this presentation, this slide holds the citation for that paper at the top. And thank you again.